When routing conductors from a cable tray into a motor control center, or MCC, several approved methods exist to ensure safe and code-compliant installation. These methods address conductor termination, physical protection, and maintaining the MCC environmental rating. Let's explore 4 common approaches. Method 1 involves a cable tray transition to conduit. Firstly, install the cable tray vertically above the MCC. This orientation facilitates a smooth transition for the conductors. Secondly, carefully cut an opening in the MCC roof for each conductor that needs to enter. The size of these openings must accommodate the conduit nipples. Thirdly, install conduit nipples with bushings in the MCC roof openings. The bushings protect the conductor insulation from abrasion. Fourthly, terminate the conductors to the MCC terminals using conduit. This provides a secure and mechanically protected connection. Method 2 describes cable tray to MCC notching. Firstly, install the cable tray vertically above the MCC similar to the previous method. Secondly, notch the top of the MCC to create an opening for the conductors. The notch should be sized appropriately for the number and size of conductors. Thirdly, install a gland plate with bushings in the MCC notch. The gland plate provides strain relief and environmental sealing. Fourthly, terminate the conductors to the MCC terminals directly from the cable tray. This eliminates the need for conduit within the MCC. Method 3 introduces a removable MCC roof section. Firstly, install the cable tray vertically above the MCC. Secondly, create a removable roof section on the MCC, allowing access to the MCC terminals. This removable section provides convenient access for installation and maintenance. Thirdly, install a gland plate with bushings on the removable roof section. The gland plate offers secure conductor entry and sealing. Fourthly, terminate the conductors to the MCC terminals directly from the cable tray through the removable roof section. This method is particularly useful for large conductor bundles. Method 4 involves a transformer secondary terminal block. Firstly, install a transformer secondary terminal block outside the MCC. This terminal block acts as an intermediary point for conductor termination. Secondly, terminate the conductors from the cable tray to the terminal block. This simplifies the connection process and provides a clear demarcation point. Thirdly, run conduits from the terminal block to the MCC terminals. This method uses conduit for the final connection to the MCC. Several common considerations apply to all methods. Firstly, ensure that the conductors are rated for the cable tray environment. This includes proper insulation type, temperature rating, and ampacity. Secondly, always follow the MCC manufacturer's instructions for cable entry. These instructions provide specific guidance for the particular MCC model. Thirdly, provide adequate space for conductor bending and terminations. Sufficient bending radius prevents stress on the conductors and terminals. Fourthly, seal all openings around the conductors to maintain the MCC NEM enclosure rating. This prevents the ingress of dust, moisture, and other contaminants. Fifthly, ensure compliance with applicable electrical codes and standards such as the National Electrical Code, or NEC. It is crucial to select the appropriate conductors for the application. Conductor selection involves several factors, including ampacity, voltage rating, insulation type, and environmental conditions. The NEC provides tables and guidelines for determining the appropriate conductor size based on the load current and other factors. Ampacity refers to the current carrying capacity of a conductor. It is the maximum amount of current that a conductor can safely carry without exceeding its temperature rating. The NEC provides ampacity tables that list the ampacity of different conductor sizes and insulation types. These tables take into account factors such as ambient temperature, number of conductors in a raceway or cable, and the type of insulation. Voltage rating refers to the maximum voltage that a conductor can safely withstand. Conductors must be selected with a voltage rating that is equal to or greater than the system voltage. Insulation type refers to the material that surrounds the conductor and provides electrical insulation. Different insulation types have different temperature ratings, moisture resistance, and other properties. Common insulation types include THHN, THWN, and XHHW. Environmental conditions refer to the conditions in which the conductors will be installed, such as temperature, moisture, and exposure to chemicals. Conductors must be selected with an insulation type that is suitable for the environmental conditions. For example, conductors installed in wet locations must have a moisture-resistant insulation. When routing conductors through cable tray, it is important to consider the fill requirements specified in the NEC. The NEC limits the amount of space that can be occupied by conductors in a cable tray to prevent overheating and ensure proper ventilation. The fill requirements vary depending on the type of cable tray, the type of conductors, and the number of conductors. Cable trays are typically available in several materials, including steel, aluminum, and fiberglass. Steel cable trays are the most common type and are suitable for a wide range of applications. Aluminum cable trays are lighter than steel and are corrosion resistant, making them suitable for use in harsh environments. Fiberglass cable trays are non-conductive and are resistant to chemicals, making them suitable for use in corrosive environments. Cable trays are also available in several different designs, including ladder type, trough type, and solid bottom type. Ladder type cable trays have open rungs that allow for easy access to the conductors. Trough type cable trays have a solid bottom with ventilated sides. Solid bottom cable trays have a solid bottom and sides, providing maximum protection for the conductors. Grounding is an essential aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock. The NEC requires that all electrical equipment be properly grounded. Grounding can be achieved by connecting the equipment to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode must be properly sized and installed in accordance with the NEC. In addition to grounding, bonding is also important for electrical safety. Bonding is the process of connecting together all of the metal parts of an electrical system to create a low impedance path for fault current. Bonding helps to equalize the voltage between different metal parts, which reduces the risk of electrical shock. The NEC requires that all metal parts of an electrical system be properly bonded. Bonding can be achieved by using bonding jumpers or by connecting the metal parts to a common grounding point. Overcurrent protection is another essential aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When an overcurrent occurs, the overcurrent protection device will trip or blow, interrupting the flow of current and preventing damage to the equipment and wiring. The NEC requires that all electrical circuits be protected by overcurrent protection devices. The overcurrent protection device must be properly sized to protect the circuit from overloads and short circuits. Short circuit current rating, or SCCR, is a critical parameter for electrical equipment. The SCCR indicates the maximum short circuit current that the equipment can safely withstand without causing damage or creating a hazard. It is important to select equipment with an SCCR that is equal to or greater than the available short circuit current at the point of installation. The available short circuit current is the amount of current that would flow in the event of a short circuit. It is determined by the impedance of the power source and the conductors. The NEC requires that electrical equipment be marked with its SCCR. Coordination of overcurrent protection devices is important to ensure that the overcurrent protection device closest to the fault will trip first, minimizing the extent of the outage. Coordination can be achieved by using different types of overcurrent protection devices with different time current characteristics. The time current characteristic of an overcurrent protection device describes how quickly the device will trip in response to different levels of overcurrent. Selective coordination is a type of coordination that ensures that only the overcurrent protection device closest to the fault will trip, while all other overcurrent protection devices upstream will remain closed. Arc flash is a dangerous electrical hazard that can occur when a short circuit creates an electric arc. Arc flash events can generate extremely high temperatures and pressures, which can cause severe burns, injuries, and even death. The NEC requires that employees perform an arc flash hazard assessment to determine the potential arc flash hazards in their workplace. The arc flash hazard assessment must take into account factors such as the available short-circuit current, the clearing time of the overcurrent protection devices, and the working distance from the equipment. Based on the results of the arc flash hazard assessment, employers must implement measures to protect employees from arc flash hazards, such as providing personal protective equipment, or PPE, and training employees on safe work practices. PPE for arc flash protection includes arc-rated clothing, gloves, face shields, and other protective gear. The level of PPE required depends on the severity of the potential arc flash hazard. Training on safe work practices is essential to ensure that employees understand the hazards of arc flash and how to protect themselves. Safe work practices include de-energizing equipment before working on it, using insulated tools, and maintaining a safe working distance from energized equipment. The NEC contains many requirements for electrical installations. It is important to be familiar with these requirements to ensure that electrical installations are safe and compliant. The NEC is updated every 3 years, so it is important to stay current with the latest edition. The NEC is a complex document, and it can be difficult to understand all of the requirements. There are many resources available to help you understand the NEC, such as training courses, books, and websites. It is important to consult with a qualified electrical professional if you have any questions about the NEC. Proper planning and execution are crucial for a successful and safe electrical installation when interfacing cable trays to MCC. By considering the available methods, adhering to manufacturer's instructions, and complying with the NEC, you can ensure a reliable and code-compliant system. Furthermore, always prioritize safety and seek guidance from qualified professionals when necessary. It's important to also consider the National Electrical Manufacturers Association, or NEMA, enclosure rating. This rating defines the degree of protection provided by an enclosure against environmental factors such as dust, water, and ice. Maintaining the MCC NEMA rating is crucial for ensuring its reliable operation and preventing damage to the internal component. When selecting a cable entry method, consider how it will affect the MCC NEMA rating. Properly sealing all openings around the conductors is essential for maintaining the enclosure's integrity. Gland plates, bushings, and sealing compounds can be used to achieve a tight seal and prevent the ingress of contaminant. Also, consider the type of environment in which the MCC is located. For example, if the MCC is located in a wet or dusty environment, it is important to select a cable entry method that provides a high degree of protection against these elements. The selection of appropriate hardware and components is crucial for ensuring a safe and reliable electrical installation. Choose components that are rated for the intended application and that meet or exceed the requirements of the NEC and other applicable standards. Inspect all components before installation to ensure that they are free from defects and damage. Follow the manufacturer's instructions for installation and use. Use the correct tools and techniques for the job. Avoid over-tightening or under-tightening connections. Properly support and secure all components to prevent movement or vibration. Conduct thorough testing and inspection after installation to verify that the system is functioning properly and that all connections are tight. Maintain accurate records of all installations and inspections. Regularly inspect and maintain the system to ensure that it continues to operate safely and reliably. When working with electricity, always follow safe work practices to protect yourself from electrical shock and other hazards. De-energize equipment before working on it whenever possible. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as gloves, safety glasses, and arc-rated clothing. Maintain a safe working distance from energized equipment. Be aware of your surroundings and avoid distractions. Never work alone. If you are not qualified to perform electrical work, hire a qualified electrical contractor. Proper conductor support and management within the cable tray and as they transition to the MCC are crucial for ensuring long-term reliability and preventing damage to the conductors. Use cable ties, straps, or other suitable methods to secure the conductors within the cable tray. Avoid over-tightening the cable ties, as this can damage the conductor insulation. Maintain adequate spacing between conductors to allow for proper ventilation. Support the conductors as they transition from the cable tray to the MCC to prevent strain on the terminations. Use bushings or other protective devices to protect the conductors from abrasion as they enter the MCC. Ensure that the conductors are properly labeled to facilitate identification and maintenance. The number of 750 MCM conductors mentioned, 18 in total, is a significant amount and requires careful planning and execution to ensure safe and code-compliant installation. The chosen method must accommodate this quantity of conductors while maintaining adequate spacing, bending radius, and termination space. It is crucial to consult the MCC manufacturer's specifications and the NEC to determine the appropriate conductor fill requirements and to ensure that the selected cable entry method is suitable for this large number of conductors. Consider using multiple smaller conduits or a larger cable entry opening to accommodate the conductors. Ensure that the MCC has sufficient internal space for termination of all 18 conductors. If necessary, consider using a larger MCC or adding additional termination point. Also, remember to properly direct the ampacity of the conductors according to NEC Table 310.15 current if the number of current carrying conductors exceeds 3 in a raceway or cable. In addition to the physical installation, proper documentation and labeling are essential for maintaining a safe and reliable electrical system. Create detailed drawings and diagrams showing the location of all conductors, cable trays, and MCC. Label all conductors, cable trays, and MCC with their corresponding circuit numbers and functions. Keep accurate records of all inspections, tests, and maintenance performed on the system. Make this documentation readily available to qualified personnel. Periodic inspections and maintenance are essential for ensuring the continued safe and reliable operation of the electrical system. Regularly inspect cable trays, conductors, and MCC for signs of damage, wear, or corrosion. Tighten any loose connections. Replace any damaged or worn components. Test the grounding system to ensure that it is functioning properly. Verify that all overcurrent protection devices are properly sized and coordinated. Clean cable trays and MCC to remove dust, dirt, and other contaminants. Keep the area around cable trays and MCC clear of obstructions. Address any potential hazards promptly. It is also helpful to implement a preventative maintenance program to identify and address potential problems before they become serious. This program should include regular inspections, testing, and cleaning. By following these guidelines, you can ensure a safe, reliable, and code-compliant electrical system for connecting cable tray conductors to an MCC.